Okay guys, so as we look at different polynomial function graphs, and the idea will be that we will be able to graph them on our own, we're going to be exploring what we refer to as the end behavior of the graph. And what we mean by end behavior, kind of like when we look at this quadratic polynomial that I've got graphed here, we can see that on the left side here our y values are increasing or rising, and on the right side of the graph our y values are increasing or rising as well. So when we talk about end behavior, we're really talking about what the left and right side of our graph are doing in terms of rising or falling. So with something like this here, I can see that my graph rises on both sides. If I were to turn this one off and say turn on this first degree polynomial that I made, this linear thing, we can see that on the left side of our graph we are rising, but on the right side of our graph we are falling. Okay. How about our cubic function that I've just kind of made up here? We can see this nice smooth polynomial curve that goes through this little bend here in the middle, but with respect to the outsides, the left side here decreases without bound and our right side increases without bound. So we fall on the left and we rise on the right. And then last but not least, we can see this last polynomial function that I created, this nice little bendy curve. It may do some fun things in the middle here, but with respect to the outside, it falls on the left and it falls on the right. So what I've done here is I've actually created some graphs that illustrate all four different possibilities for end behavior. We could either rise and rise on the left and the right. We could fall and fall on the left and the right. Or we could rise on the left and fall on the right. Or we could fall on the left and rise on the right, as in our green graph right here. So with all of those possibilities being named, our job is to, just by looking at the function, be able to tell the audience, hey, excuse me, what's the end behavior of our graph? And so this right here is directly connected to what we're going to call the leading coefficient test. And so this little chart here, we're going to write above it here, the leading coefficient test. Actually, let me put this down here. The leading coefficient test. What that means is if we have our polynomial and it's written in standard form, then we could use the leading coefficient tests to tell us about the end behavior of the graph just by knowing the leading coefficient here. So let me fix my zoom. Apologies, 110. Okay, let me go back to my pen tool. So leading coefficient test, we're going to look at two things here. We're going to say leading coefficient and degree. And so in order to explore this, what I'm going to do is I'm actually going to open up another graph that I've made in the past here. And it illustrates what we call a power function. Now a power function, let's see here, it's just a function that is a polynomial, but only has one term being raised to a power. So that's why we refer to it as a power function. But basically in this one-term polynomial, what I want you to recognize is that it's already then in standard form and that our leading coefficient right now is equal to 1. And right now our degree, which is our highest exponent on any x, is first degree. What I want you to see is the behavior on the left compared to the behavior on the right of our graph here as the degree changes. And so when the degree is 1, it looks like we fall on the left and rise on the right. When I change this to 2 here, we all of a sudden get some quadratic graph that rises on both the left and the right. How about third degree? Third degree gives us this cubic graph here that falls on the left but rises on the right. And if we go to fourth degree, we again have something that rises on the left and rises on the right. So what I want you to notice is that as I alternate my degree here, the end behavior on the left and the right changes depending upon what the degree is. And what we notice is that every time the degree is even, second degree quadratic, fourth degree quartic, sixth degree, eighth degree, 10th degree, the behavior on the left side of the graph always matches the behavior on the right side of the graph. And that is to say that if the right side rises, then the left side also rises if the degree is even. Now if our degree is odd, what we keep noticing is odd degree polynomial graphs have opposite behaviors on the left and the right. So if you're falling on one side, you'd be rising on the other if your degree is odd. And this even occurs with linear graphs. And so one thing that we want to make sure that we know about this is this, our degree. If our degree is even, then we're going to have the same behavior on the left and the right side. Okay? And if our degree is odd, we're going to have opposite behaviors on the left and right hand side. And so that is actually, as a matter of fact, illustrated in this chart up here. We would see that if our degree is odd, okay, in either of these instances, what we see are graphs that either fall on the left and rise on the right, or rise on the left and fall on the right. And if our degree is even, we have both rising on the left and the right, or both falling on the left and the right. So that's a neat thing, to be able to look at the degree and just determine whether the left and the right hand side should behave the same or not. Now the neat thing about this is I'm just kind of flipping through degrees here, but I want you to notice is that as I do this, one side of the graph is always rising, and in this particular case, the right side is always rising. If I actually wanted to switch that behavior, all I would have to do is go take my leading coefficient and switch its sign so that, say, it is negative. And so what I want you to see is that when we have a negative leading coefficient, we still have, if it's an even degree, the same behavior on the left and right, and if it's an odd degree, opposite behavior on the left and the right. But you'll notice that always the right side of the graph is falling in this case. And so the reason why we give this the name the leading coefficient test is because if our leading coefficient is positive, okay, positive, then we're going to say the right-hand side rises. And if our leading coefficient is negative, okay, then our right-hand side falls. The neat thing, though, is the leading coefficient test always tells us about just how the right-hand side behavior of our graph is going to behave. And so you could see something like these up here now, excuse me, where it says our degree is odd. If our leading coefficient is positive, then that means that the right side of our graph was rising, and because the degree was odd, then that would tell us that the left-hand side would have to fall. Likewise here we say if our leading coefficient is negative, our right side of our graph definitely falls, but because the degree was odd, the left side would have to behave differently from the right side. But again, the right-hand side of the graph is always determined by the sign of your leading coefficient. So to go back to these graphs that I had created in the first place here, let me turn them all off. These are all written in standard form so that our exponents go in decreasing order here. But what I want you to notice is that this first equation has a positive leading coefficient, and so automatically I could tell you that the right side of my graph must rise. And because the degree is even, we would know that the left-hand side would have to behave the same way. Looking at this next one here, a negative leading coefficient would mean the right side of our graph has to fall, and because our degree here, which is really this is x to the first power, then we would have that being odd would mean the left side of the graph would have to behave opposite. So we could see that we fall on the right because of the negative leading coefficient, and we're opposite on the left just because of the odd degree. Here we have a positive leading coefficient. Positive leading coefficient means the right side is going to rise, and because the degree is odd, the left side will just be opposite of the right. So when I hit and highlight this again, you can see we definitely rise on the right and fall on the left. And then last but not least, we say that this has a negative leading coefficient, so the right side would have to fall. And furthermore, because the degree is even on this, the left side would have to do the same thing as what the right side did, which, so if the right is falling, we would say that the left would also fall here. So this is a really handy tool in order to determine what your graph does on its ends. And what we mean by end behavior is left-hand side and right-hand side behavior. What the graph does in between the ends is up to what we get for when we plug in some x values and get some y values back. So let's take a look at using this leading coefficient test to describe the end behavior of our graph and function. So first things first, on number 16 here, I want to check to see that we're in standard form. And it looks like because we have our x to the fourth and then x to the third, x to the second, x to the first, and x to the 0, or just our constant term here, then it looks like we're already in standard form. So our leading coefficient is definitely a 6. And our degree here looks like we have a fourth degree thing. We would call this a quartic polynomial. Well, the fact here is this. Because our leading coefficient is positive, we know that the which side always follows the leading coefficient? It's right, the right-hand side. So we would say that because our leading coefficient is positive, right-hand side rises. In terms of what this does here, now it's a mystery to us, but all we have to do is go look at the degree, and because the degree is even here, we would say, well, then it has to do the same thing on the left as it does on the right. And so I'm going to write this in here. Now the thing that's a little bit different is this notation that you see here. So determining this part was pretty easy. Right-hand side rises because of the positive leading coefficient. Left-hand side matches it because of the even degree. What we're going to look at now is how we notate this, or how we write it. And so what you're going to see here is this. It says as x arrow negative infinity. And what we really mean is as x approaches negative infinity, what are the y values doing, or our f of x values doing? Likewise, as x goes to positive infinity, what are our y values doing? So in each of these graphs that you see on the left here, I want to point out that on every single one of them, we're saying our y values are getting close to this as x approaches negative infinity, and our y values are getting close to this as x approaches positive infinity. And when we say x approaches negative infinity or positive infinity, what we're really saying is as our x values that we're plugging into this function go really far to the left, then what are our y values doing? And in this particular case, we could say as the x values I'm plugging into this graph go to the left here, our y values are actually going down forever and ever, and so they approach negative infinity. Likewise, we see that as x goes to positive infinity, this really means as we go really far out on the right, what are our y values doing? We can see that our y values start climbing and never stop climbing, or they rise forever and ever. So we say that as x goes to the positive infinity, or on the right here, our f of x values also go to positive infinity. And so this is going to be true for all these graphs. we're always going to say as x goes to negative infinity, as x goes to positive infinity. And what we're really saying is as we go to the left and as we go to the right, what are our y values really doing here? And we're either going to indicate that they either go to positive infinity, like this graph does here, or y values go up for every number, or that they're going to go to negative infinity, like this one always goes down to negative infinity. On these next graphs here, we see positive infinity and positive infinity for our y values on this particular graph as x gets to the left or the right. And as x goes to the left or the right here, we see that both of our y values on both ends of the graph, our y values would approach negative infinity. So once we've indicated this up here, the idea is that we're going to have to actually write in what our y values are approaching. And so this is a little bit easier once you've got this part. We'll basically just say either positive or negative infinity to correspond to whether we're rising or falling. And so because we're rising on both sides of this graph, we would say then as x goes to the left here, as x goes to negative infinity, our y values are approaching positive infinity because our graph would rise on the right or on the left side. And as x goes to the right, okay, as x goes to positive infinity on the right side of our graph, our y values are also going to positive infinity here, okay? So pretty easy to do if we know what our sign on our leading coefficient is and our degree. So let's take a look at h of x here on number 17. First of all, let's make sure that we're in standard form. I notice that my exponents are all in decreasing order here. So we would say our leading coefficient here in this case is a negative 5 and our degree is a 9. So let's start with this. Our leading coefficient, what would that tell us about our graph if it's negative? Is it the right-hand side or the left-hand side that falls looking at our leading coefficient? And again, remember that our leading coefficient always corresponds to what the right-hand side of our graph is going to do. So if our leading coefficient is positive, right-hand side rises. If our leading coefficient is negative, right-hand side falls. Because our leading coefficient is negative, well then our right-hand side would have to fall. And in terms of our degree here, it's a 9th degree thing. That's an odd degree. And so with odd degree things, we would see that our opposite behavior would be apparent here. So our left-hand side compared to the right would have to rise compared to the fall. So to fill these in, we'd say as x gets really close to negative infinity, as we go to the left here, our y values are going to positive infinity. And as x goes to positive infinity on the right here, our y values are going to negative infinity. Okay? So let's take a look at 18 and 19 here. I want you to pause the video, okay, and actually make sure that you have this in standard form first and identify the leading coefficient and the degree. Once you've done that, go ahead and determine your end behavior of the right side first and then use that with your degree to find the left side behavior. And then we'll talk about what we get for these values over here. Okay, so for 18g of x, we'll notice that this isn't in standard form yet. We actually have to rearrange this so our exponents are in decreasing order. So I noticed that negative 7x to the 6th would come first, followed by our, looks like x is to the 4th next, minus 5x to the 4th here, plus 7x to the 3rd, okay? Then we have plus x squared minus 9x plus 2. Now that we have this written out in standard form, our negative leading coefficient is negative 7 here. Excuse me, and our degree is a 6th degree thing. So knowing that the leading coefficient is negative tells us instantly the right-hand side has to fall. And because our degree is even, we know that instantly, or next to instantly, or I suppose the left side would have to be the same as the right. So as x goes to the left here, as x goes to negative infinity, our y values go to negative infinity on the left and fall. And as x goes to positive infinity, our y values on the right also fall and approach negative infinity. And then for this one here, you should have determined that this also is not in standard form. We'd have to rewrite this in standard form first. So we would have 4x to the 5th, okay, 4x to the 5th. Looks like minus 3x to the 4th. We'd have minus 2x to the 3rd, plus 12x squared minus 4. So our leading coefficient here is 4, and our degree is 5th degree. And because our leading coefficient is positive, well then the right side definitely has to rise. And because our degree is odd, okay, well then the left side would have to be opposite of our right side. So we have a falls and rises graph on the left and right hand side respectively. So on the left side, as x goes to negative infinity, we would decrease to negative infinity for our y values. And as x goes to the right, it gets very large. We say our y values are increasing without bounds, and they go to positive infinity. So for 21 and 22 here, here's what I want to see. In terms of degree and leading coefficient, what I want to do is I want to figure out what could we determine about the degree and leading coefficient just by looking at the graph here. And because I can see that on 21 here, the left side rises and the right side falls on this graph, well, first things first, I can tell you that our leading coefficient, would it have to be positive or negative looking at the right side of our graph? Well, our leading coefficient would have to be a negative value. The only way we could determine this is to look at the right-hand side behavior, and it's definitely decreasing. So we would say negative leading coefficient. And because the degree here, we're looking at it, I can't tell you what the degree is, but I know that the left and right-hand side behave opposite of each other. So because they are opposite, okay, we would have to have an odd degree. Okay. So you can see how we can use our end behavior of a graph to work backwards to make some assumptions about the degree and leading coefficient. I want you to figure out the same things here. What could you tell me about the degree and the leading coefficient given that the left-hand, right-hand side behavior are the same and the right-hand side behavior is specifically rising? Cheers.